Okay, so today's lecture is 4.4 on coordinates and bases. And I have to start first explaining to you what the basis is. Now, let's remind you a bit where we have. We talked about vector spaces, so V is a vector space. And for us, we think very often of vector spaces R square, R cube, and so on. Okay, and then if we had a collection of vectors, let's write it as V1, Vm, we don't know how many, many, then we had two things we could say about this collection. The first thing was the span of S. And remember, that was all linear combinations of these vectors. Of these M vectors that you have. And we know that this is a subspace. Okay, that was one thing. And the other thing we discussed, and that was in the previous lecture, is S is linearly independent. Linearly independent. And that meant that no element in S is a linear combination of the others. So to say, the quickest way to say that there are no superfluous linear combinations. Okay, one way to say this was, and that's how I write it down, is that we have the only way that you could write a linear combination and have as a result the zero vector. There's only one way to do that. Then we had that is by just taking all the scalars equal to zero. Of course, if you take them equal to zero, you get the zero vector, right? The zero vector, sorry, I said vector there. But sometimes you can write a combination of vectors that is like twice one and 3 times the other one and so on, that gives still the zero vector. And then you would be linearly dependent. So linear independence says you cannot do that. Okay, so that's a very good condition. Now, going back to the span of S, now we know that these are vectors in our vector space, right? We don't know where we're living, so this is this part of this vector space here. But what happens if the span would be everything? So we are now thinking about choosing an S that has the property that it is linear independent, but you also want the property that this is everything. And if these two conditions are held, then we say S is a basis. So we call S a basis if every vector in V is a linear combination of these vectors and these vectors are linear independent. Now, I can say this even better. Let me say it slightly different. So we say that S is a basis means that any vector of V, of our vector space, can be written as a linear combination of these vectors. So again, my vectors were V1, Vm. I'm going to do concrete examples shortly so that you see what I really mean here. Linear combination of these vectors in S. So that's what I'm saying now, that any vector of V can be written as a linear combination of Vn. That's saying here that the span is everything, right? That's what I said now yet. So what is this linear independence then says? Can be written in one way only. Can be written, and so I'll write it in a little bit, in a unique way as a linear combination of V1 and V1 to Vm. So that's this condition. Okay, so perhaps I'll do this other color. To be a linear combination, that is given here, that's this condition. To be written in a unique way, in a unique way as a linear combination, that is this condition. So that's what a basis is. That means, so it just simply says that if you have a basis for a vector space, then take any vector and you can write it in one way and one way only as a linear combination of these given basis vectors. Okay, let's do the examples. Now, this is something, it's a topic that we're going to discuss in length more in the next sessions as well. So we're not going to do everything about it yet. And so we're going to concentrate for now on vector spaces that we know. These are square, are cube, and so on. So let's figure out what this means in these cases. So let's look at a very, very simple example. In R square, I claim that the following two vectors, I'm going to write them as well, no, let's write them as, so we call them I, that was, and J was 0, 1. Remember, if I would put this on the Cartesian plane, my two vectors, I use them at somewhat different colors. This would be I, right? And then the J would be this vector. That would be J. You agree with that? Okay, yeah. And so what it says is now any vector can be written in a unique way as a linear combination of I and J. Now we know how to do this. Remember, we discussed this in an example last time. Suppose we have a vector here, say, let's take the vector, I'm going to make it a little bit, suppose we have the vector here whose endpoint is 3, 2. So this is the point at 3, 2. So we have this vector here. Now it's very easy to write this as a linear combination of I and J, namely U is 3 times I, this 3, plus 2 times J, this 2. Just the coordinates, okay? You see where coordinates and bases are there linked, and we will talk about it a bit later. And this is the only way I can do it, because these are exactly, 3 and 2 are exactly the coordinates of that endpoint, so it has only one set of coordinates, so this shows that this is a basis, so this is a basis. And this is sometimes, because it's so simple, we call it the standard basis. But the point is that these are not the only ones. So now comes the question, then, okay, I'll give you, I'm claiming so that this is also a basis. So let's take the vectors 1, 3 and the vector 2, 4. Now that's not entirely clear that if I now give you, what this says is, I claim that this is a basis. So claim, or let me just say it, is a basis. But now, that's what I'm saying. So what should I, if I want to prove this, so let me put it as a question mark, what should I do? Well, I have to show that every element, every vector in the plane can be written as a linear combination of these two. Now, we discussed how we can figure out that something is in the span of two vectors, right? That meant that we would look at the linear system of equations, and then, so let's take an example of a vector that I want to show that it's in there. Well, let's try to show that 1, 0. If this is a basis, then I should be able to write this vector, this is the vector I, let's use the same letter as before, that this is a linear combination, let's call this U and let's call this V, right? So if this would be a basis, then I should be able to write I as a linear combination of these two guys. Now, how do we do this? Remember, this was, you can think of this as, if you think of these as column vectors, so 2, 4, and this is 1, 0, right? So what I'm saying is that an A times this vector plus B times this vector should be equal to that vector. Now, that also meant, if you can write it in matrix notation, this means that we have this equation, a linear system of equations, and how do we solve that? Well, what we do, so the question is can this be solved? Right? Are there A and B that solves this equation, and how did we solve? Or how did we figure this out? Well, we took the matrix 1, 3, 2, 4 and row reduce it 1, 0. And add the augmented column and then row reduce, and then we have to show that that there is no pivot in the last column. So, but this is very simple here, right? So I'm going to quickly do it, but I'm going to show you shortly a better method. So this is our pivot that I'm going to use. So I'm going to do row 2, replace row 2 minus 3 times row 1. I hope everyone sees why I'm doing that. So that's 1, 2, 1, 0. So this is times negative 3, right? So minus 6 plus 4 is negative 2, and then here we get negative 3. Now, okay, so this is my pivot. What about the next pivot? Well, this is the position of the next pivot. I have to divide by negative 2 to make it a 1, but it tells me already I'm done now, right? Because it says, oh, you have a pivot here, you have a pivot there, and that's it. There are no other pivots, so your system is solvable, okay? And then that was, so yes, so it is, so this can be solved, but of course I just checked for this one vector, perhaps another vector doesn't work it for, right? So now what about, is it true that I can write this only in one way? Well, let's think about what that was. That was in 2.3 we discussed linear independence, and what that meant was that if you want to show that something is linear dependent, then you have to show that if you row reduce the matrix, and indeed, so for row independence, linear independence, what do you do now? Well, you look at the same matrix, but this time you're asking, how can I write the zero vector? So I'm not asking about this any of these vectors, I'm really asking about the zero vector. Remember, this is how linear independence discusses about zero vectors. Go back to the previous lecture if you forgot why that is the case. So we row reduce again. Now, of course, it's the same row operation. So if I do this, I get 1, 2, the back column is always zeros, 0, negative 2, and I get again the same pivots, of course. And what's linear independence was there are no free variables. Because if you had free variables, then you had more solutions. But if you had no free variables, there was only one solution. So this tells me that it is linear independent. So these two guys are linearly independent. I have now shown an example that it is solvable, that you can write a vector in a linear combination of it, but if you think about it, any vector can be written as a linear combination. What does any vector mean? Well, that means that this column could be now anything. But I still do the same row operations, I still get the same, I still get this echelon form, but now this, okay, let me write it now in something, we don't know really what these guys are, there's some stuff here, right? We calculate with some other stuff, but it doesn't matter what it is, we have our two pivots, and this means that the system is solvable, okay? So this shows that this is a basis. Now that's a long-winded discussion of showing that this is a basis. I can do it much quicker, because what I'm trying to show is, look what the echelon form is. What I'm trying to say is, if I would do the echelon form, or rather even the reduced echelon form, which I didn't do here, but you can do, and you can see that what I'm saying is true. If you would do the reduced echelon form of this matrix, then actually you get the identity matrix, right? Because it means, this says you have to have pivots. No pivot can be in the last column. So in other words, all your pivots must be in the matrix itself. And this says there are no other things. Because if you would have a variable, if one of these columns would not be a pivot, would not contain a pivot, that would give you a free variable. So what I'm saying is that this is a basis, and that's true in general, for R square, for R2, and so on, is if the corresponding matrix in reduced echelon form is the identity matrix. But that meant, if you go back to what it means, it just means that this matrix was invertible. So, and then what that meant, how did we check that? Again, very easy. That meant that the determinant was not zero. Okay, so I said a lot of things now, but what I came, if you now go back and see what is all the things that I said, is basically this. We had these two vectors, in this case it was 1, 3, and 2, 4. I put them in, this make a matrix, right? So remember, to do this, you have to write the vectors in columns. That's a bit confusing, perhaps, that between rows and columns, but for this to work, you have to write it in columns. Although actually, this particular case, it doesn't matter, but in general it does. So this is the matrix that you get from the two candidate basis vectors, and what we're saying now is that these two guys is a basis, is the same as saying that the determinant of A is not zero. So these two conditions are the same, which we do sometimes with this double arrow. Why? I repeat quickly, the determinant non-zero means that this matrix is invertible. That means that this matrix, if you row reduce it, then you get the the echelon, its row reduced echelon form is the identity matrix, which means that are exactly, as in this case, two pivots, and therefore there are no free variables and any solution is solvable. And now they can do this in any dimensions. So let me give an example now in dimension 3. And we're not going to do the long. Now we have this shortcut of doing this. So let's ask the question here. So now in R2, so now on, that's how we're going to do these things. So here are my three vectors. V1 is the vector 1, 2, 1. V2 is the vector 2, 9, 0. And then V3 is the vector 3, 3, 4. So the question is this the basis? Notice you might say, why are you taking 3 and not 4 or 2? Well, that's something that we're not gonna cover it in detail, but what it means is that you're gonna a basis. How many elements are there going to be basis? Well, that is going to be, in this case, you saw there are two elements, and this was the basis of our square. And we say a two-dimensional space, and dimension is exactly that, the number of elements in the basis vector, in the basis. Now that we are here in scroll up a little bit. In R3, we're going to have 3 dimensions, and therefore we're going to have 3 basis vectors. Because after all, we need a square matrix, right? We're going to check that some. Remember, I'm going to put this, what I'm going to do. So the question is this a basis? Is this a basis? Is this a basis? And how do you solve this? Well, you take the matrix formed by the columns. You write these vectors as columns. So 1, 2, 1, 2, 9, 0, 3, 3, 4. So make sure that you don't write it as rows here, but as columns. And what we need to show now is, the question is the determinant of A non-zero? Okay, and as I said, we need the square matrix, so that's why we need 3 vectors, size 3 here. Okay, and so in R4 you would need 4 vectors, right? Okay, yeah, we'll do an example later. So okay, so how do you figure this out? Well, we know how to calculate the determinant, so let's quickly do this. So we have to calculate this thing, the determinant, right? We do this with the vertical bar. Okay. I don't want to do expansion here. I don't have enough zeros, so I'm going to first do row operations. I'm going to use this as a pivot. So the row operations that I'm thinking about are R2 minus 2 times R1 and R3 minus R1. I hope everybody now understands why. So get 1, 2, 3. Let me do it in black. I get 1, 2, 3, nothing happens. The next row I multiply -2, 5, -3, and I get 0, -2, 1. Okay. Now we expand along column 1, and since the pivot is in the plus position, I'm gonna go quick now. What I'm left with is this cofactor, which I just calculate by the formula. That is 5 times 1 minus plus 6, so 11, which is non-zero. So yes, this is a basis. So this is a basis. Okay, and as simple as that. So it's actually much simpler, as you'll see, than checking linear independence or checking spans, calculating spans. But this is because we're talking about our cube itself. R to the third, right? But remember, R to the third, that's the 3-dimensional space, but there are planes in there. So a basis of a plane, that's a trickier question, but we'll do that next time. Okay, so let's do one more example in R to the 4. So now how many vectors should I have? If I want the basis, it can only be if I have 4 vectors. So here are my vectors that I'm proposing. V1 is 0, minus 3, 1, 0. V2 is sorry. Let me erase this. I copied it wrong. So this is 3, 0, 1, 6. V2 is 1, 1, 0, 2. V3 is 0, 4, 1, 3, and V4 is 0, 4, 2, 1. Okay? So, question, is this a basis? Solution, put it all into a matrix and calculate the determinant. Let me write it immediately as a determinant. So we want to calculate this here. But remember, these becomes the rows, the columns. So 3, 0, 1, 6, etc. 1, 1, 0, 2. That's a small thing you have to be pay attention to. 0, 4, what am I doing? Sorry, I got a bit confused. Yeah, 1, 3, and 0, 4, 2, 1. Okay. I don't see enough zeros. The first row has 2 zeros, but I only do this when I have only one non-zero element in the row column. So I'm for expansion. So I'm going to do first using this one to make zeros everywhere. All right, so let's do that. So what are the operations here? Row 1 minus 3 times row 3, and row 4 minus 6 times row 3. Right, I'm working now with this pivot. What does this give it? So for this one, negative 3 times, so that is a 0 there, that's a 1, that's a negative 3, and that's a negative 6. Don't touch this row, neither do I do anything with this row. And then the last row, so now it's negative 6. I get 0, 2, negative 6 plus 3, that's negative 3, and negative 12 plus 1 is negative 11. Okay, good. That means I'm going to expand here, but remember plus minus plus. Oh, it's a plus sign. So this is the expansion along column 1. And so that is plus 1, okay? Plus and the 1 here. Let me write it so that you remember where it comes from. And then I look at the cofactor. That is 1, negative 3, negative 6, 1, 4, 4, 2, negative 3, minus 11. Again, let's do row reduction. So what I have in mind here is using this pivot now. Row 2 minus row 1, and row 3 minus 2 times row 1. What I get, I'll do it down here. So 1, negative 3, negative 6. I get a 0. So I'm multiplying this with negative 1, right? So this is 7, 10. And now I'm multiplied with negative 2, 0, 6 minus 3 is 3, and then 12 minus 11 is 1, okay? And again, expansion along column 1. This means it's all 1, so there's nothing left. So what is left is 7, 10, 3, 1. That is 7 minus 30, that's minus 23, which is non-zero. So yes, that was a basis. Okay. Now you could of course have also things that are not a basis. For that, for instance, let's do an example here of that. Well, a quite simple example, similar example here. Let's see. Give me a sec here. I want to get the right numbers correctly. I get 1, negative 2. Sorry, 1, 2. Okay, so let's take the vectors here. I'm going to write them already in columns. 3, 1, 3, 0. No, sorry. Give me a sec. Yeah, 3, 1, 0, 1. 0, 1, 4, 2, 1, 0, 1, 1, 1, 0, 1, 1, and the last one is 6, 2, 3, 2. Well, they look quite different. Well, so you think, oh, they look for different, so there will probably be a basis, but okay, well, let's see. Okay, so let's do this. So question again, is this a basis? That means what we have to do is calculate the determinant of the matrix. Now everything is already in columns, so it's this matrix now. 6, 2, 3, 2. Okay, here we go. Using this one, no, right? Well, there are other options here, but that's what I'm going with. So R1 is R1 minus 3 times rho 2. I hope that by now everybody understands why I'm doing this. I'm using this one to get a 0 in this position, and that's by multiplying this with negative 3 and adding it. That's exactly what I'm saying here. Okay? And then for making this 0, that's rho 4 minus rho 4 minus rho 2. Okay? So what do I get? Start to stick here. Okay, so the first row is, so I meant to my negative 3 is 0, negative 3, 1, 0. I don't touch that row. I didn't touch anything with this guy either. So what's left is this one, right? The bottom one. So I multiply that with negative 1. I get 0, 1, 1, 0. Okay, right. So I have my pivot, be careful, this is now a plus minus, so for the cofactor I will get a negative, so column 1, right? So I get a negative here from the cofactor, and what is left is negative 3, let me write this more, negative 3, 1, 0, 4, 1, 3, and 1, 1, 0. Let's go quickly now because I have my 3 here. So I'm going to expand now column 3. That means we have a negative 3. This is a 3, the negative we had already. And what is left? Negative 3, 1, 1, 1. And so the result is negative 3 minus 1. So again, non-zero. I guess I took the wrong example. No, that can happen, but that's okay. What did I do? I wanted to give you an example where it actually comes. Oh, I see what mistake I made. I wanted to give you an example. So, okay, I did this example. So I'm going to do a similar example, but now I'm taking here negative 2. Okay, so that's the only. I'm going to change the example by making this negative 2. Well, you have this example, fine. Now I do it something else. So, okay, let me change the question then. So everything this goes. So the erasing is a little bit slow this time. I don't know why. Sometimes it goes like whoosh, everything away. Okay. Good. So here we are in black. So now I'm doing here negative 2. All right. So okay. So this is now 3, 1, 0, 1, 0, 1, 4, negative 2. Okay. I hope that this time I got it right. 1, 0, 1, 1, and 6, 2, 3, 2. You see, it's a minor detail that I changed, right? Okay, so let's see. Okay, the same thing as before. I should have perhaps not erased that part, but I do it now. Run 1, row 1 minus 3 times row 2. I'm using this pivot, right? And then row 4 minus row 2. And that gives me, let's go to black again. This gives me, so I'm doing my negative 3 here. I get 0, negative 3, 1, 0, 1, 1, 1, 0, 2, 0, 4, 1, 3, nothing changes there. And now I multiply this with negative 1 and add up. So that is a 0 there, that's a negative 3 here, that's a 1, and that's a 0 there. Okay, right? We have our column, what we can use. So column 1, I'm going to use row expansion. Again, never forget that there's a sign, right? Plus, minus, so it's still a minus sign here. Minus, the cofactor is now minus 3, 1, 0, 4, 1, 3, and minus 3, 1, 0. I actually already see that this is going to be determinant 0. But let's go on. How can I check this? Well, again, we have the 3, right? We can use our 3 to expand here with this 3. So this is column 3 really. That was, I should mark it this way. So minus 3, and then I have the cofactor is minus 3. Oh, did I get the sign right? Sorry, I should have double checked that. Plus, minus, plus, minus. No, I didn't. So there was a minus sign here also. Okay. so we get minus 3, 1, minus 3, 1, but now you see that this actually is minus minus is plus, but then inside here we get minus 3 minus minus 3, so that actually is 0. Now I said I could already see it before, because if you look at this matrix here that I had, where is it? This matrix that I obtained, you see that it has two identical rows. So that means that these rows were not linearly independent. If you have identical rows, then the matrix always is going to be not invertible. Okay, but okay, if you don't see that, as I said, you calculate and you see you get 0. Okay, so that's what the basis for our bases are. But now perhaps one more thing I want to say is now about coordinates. So let's go back to our very first example here, where we had, well, first of all, we know what the Cartesian coordinates, right? When we talk about Cartesian coordinates, we mean, really, what we mean is these are the coefficients of the linear combination where you use the standard basis. So that's what Cartesian coordinates are. You take a point, okay, and it has certain coordinates, x, y, and that means that the vector that you have, corresponding vector, is actually x times this vector I. So how to say this? Let's call this W. So this means that W is x times I, this vector, plus y times j. Okay? But what now if we remember this was the standard basis, but there were other bases. Here is an example. So what are now the coordinates of a vector in that? What do we mean with coordinates of a vector at that basis? Well, we mean the a and b that give you the linear combination. So let's do this for this 3, 2 here, okay? Okay, so I need a little bit of space, so I'm going to erase a little bit here. We now know that this is an... that this is a basis, so we don't need to verify it anymore. So let me see if I get rid of this, okay? A little bit rid of it, okay. So this is... And so, all right, we know that this is a basis. That means that we can write it, that we can write 3, 2 as a linear combination of that. So the way that we did this, remember we put these guys, these vectors as columns, and then we take the augmented column is this 3, 2, this guy here, right? So what I'm giving an example, right? I know that this is a basis, and what I'm going to do is now, this means in particular that I can write this particular vector u here as a linear combination of this basis. So I want to know what is that linear combination. So what I do is solve this system of equations, which we know how to do. So that is the row operation is here row 2 minus, replace row 2 by 3 times row 1 from it using this pivot. So we get 1, 2, 3 times minus 3, so I get 0, minus 2, minus 4. No, sorry. Minus 9, minus 7. Right? Yeah, minus 7. Okay. Well, you're gonna, when you, I said sometimes you cannot expect to not have to deal with fractions, so here you're gonna have to have a fraction. So I need to make this a 1, so what I have to do is divide row 2 by minus a half. So then the result will be 1, 2, let me go here. 1, 2, and 3, and so here we have 0, 1, and 7 halves. So divide by negative 2. Okay. So that's not that's the echelon form, but not the reduced. So I have to make now a 0 there, and for that I use that pivot, and so the row operation is row 1 minus 2 times row 2. Okay, so what we get. So I multiply this with negative 2, I said. Okay, so I get 1, 0, and then negative 7 plus 3 is negative 4, 0, 1, 7 halves. So remember, this is now, these are the pivot variables, and there are no free variables because it's a basis. And we now see that if we solve the system with in terms of x and y's, right? Or what I used, well, I wrote x and y here, okay? So this means that x is -4 and y is 7/2. But let's write it out perhaps a bit better what it really means. It means this, right? It means that these are the coefficients in my linear combination, namely the vector u is -4 times the vector 1, 3. The vector u was the vector 3, 2. Let me write it there for us, vector 3, 2. Okay, so this the vector 3, 2 is -4 times the vector 3, 1 plus 7.5 times the vector 2, 4. And we can now easily check that this is true or not, right? I hope it's true. Let's look at the first coordinate, -4 times 1 plus, that's -4 plus 7, that's 3, right? And you see the next one is also correct. Okay, good. So that's now, okay, what are these numbers now? We will call them the coordinates with respect to this new basis, the given basis. So this was this basis now, and so these are now the coordinates with respect to this basis. So that's the more general notion of coordinates, and you might find it a little bit strange. Why would you do this? But in fact, you actually know this. If you walk in Manhattan, the common way of denoting an address is giving the cross street and the avenue, right? But if you look at the grid that you have, the avenue blocks, so this you have here like 6th Avenue, and here is 5th Avenue, and well, there's no 4th Avenue, but it's called Park Avenue. So let me move over a bit. 7th, 6th, and 5th, right? 5th Ave, 6th Ave, 5th Avenue, and then you have all the cross streets, okay? There's 23rd Street, 22nd Street, 21st Street, and so on. But the distances between streets, by the way, it's 1/20 of a mile, and the distances between avenues is in general 3/20 of a mile, okay? Avenue blocks are three times as long as street blocks, give or take, and not everything is correct. But what does this mean, therefore, is that you actually have a coordinate system where the basis vector, and you can actually immediately see the basis vectors on this thing here, this and these are going to be my basis vectors, okay? And so now any address can be expressed as a number of times. This will give you the streets if you take this vector, and how many times you have to take this vector will give you the avenues. The only strange thing is, well, the numbering goes this way, right? So actually, if you now think a little bit, it's not that one. So, but what it actually is this one. So we would have to go all the way to 0th Avenue, which doesn't exist, which is, I guess, East River, or no, there are actually even other avenues over there. But okay, so we would actually, and then here we would have 0th Street, which also doesn't exist, which we call Houston Street, is actually 0th Street, right? So the actual basis actually lies here. This would give you the number of times that you have to go. This gives you the street, so this would be 23 times here, right, this vector. But then the avenues, notice it's actually not in this direction, so that was actually wrong. It's in this direction, okay? How many times you have to take this vector to the left, that will tell you the address. So here is an example of a basis. It's a very simple basis. If you want, this is length 1 and this is length 3, I said, right? So that's an example of a basis that is different from the standard basis, but the coordinates in this basis make sense. They are exactly the Manhattan street addresses. I mean, location, intersections, right? Of course, there are numbers also, but that's not what I'm talking about. Okay? And so now, so in general, of course, it gets a little bit trickier, so I don't want to do too many examples anymore. I do an example in 3.3. So we have seen that this is a basis. And so now we can express a vector as a linear combination, any vector as a linear combination of them. So let's do this, for instance, for pick something that is in the book that I know that it'll get, okay, 5, 1, minus 9. So 5 minus 1, 9. So this is now a vector in our cube, in this vector space. Since this is the basis, the definition says that this vector can be written as a linear combination in one way only, in terms of these three vectors, and the coefficients are exactly the coordinates for this vector in that new system, right? The coordinates, of course, in the old system, in the standard system, are 5, -1, 9. But in the new system, you'll see they were different. Okay, let's work that out. Again, let me try to erase here and get myself space. Although all these column operations that I did here, so I am going to have to do again, but okay. We have the time, right? You can always pause if you get tired and then come back. But please listen to the whole thing. Okay, all right, so here we go. Again, remember these have to be vectors, column vectors. And now it's basically using this as my augmented column and solving. So the row operations that we do were row 2 minus 2 times row 1, row 3 minus row 1. So go look it up where this all come from. I'm using this pivot. I get, so first -2, I get 0, 5, -3, -10, -11, and then -1 to this one. Oh, sorry, I forgot to write my first one. Yeah, and now the last row is then 0, -2, 1, 4. I have the feeling that I did something wrong, but did I? No. I don't remember anymore that we had. Oh, we were, yes, right, we were doing something else. We were calculating. We didn't do this thing. We calculated the determinant of this matrix, right? Okay, so, yeah, it's a little bit unfortunate that I have no 1 in the next for pivot anymore, right? This is my first pivot. For now, I don't have a pivot. Now, there is a trick, right? If you don't want to do fractions, there are always tricks. So perhaps it's good to do one more time, see this trick. Because you might forget this trick. But be careful, right? Don't do this just randomly start doing this. Only do this when you really, really say, okay, I need a 1 here. Please, I don't want to have fractions. So what I can do is, I take row 2 and replace it and add twice row 3 to it. Because if I'm going to add twice this number to 5, I'm going to get 1, right? Okay, so let's do that. Okay. So this is not, it's somehow not really making much progress, but at least I get a 1 here. So I'm multiplying this with 2 and add up, right? So I get a 1 and 2, that's -1, 8, that's -3, and then I get 0, -2, 1, 4. Okay, so now I have my pivot. Good. I don't have to deal with this ugly thing, with ugly fractions. So the row operation that I have to do to get this guy 0 is row 3 plus 2 times row 1. So this will be, getting away here, 1, 2, 3, 5, 0, 1, -1, -3, 0, 0, so I'm multiplying with 2 here, right? -2 plus 1 is -1, and -6 plus 4 is -2. Okay, so we have a pivot. Oh, I need the -1 here. So the row operation I'm going to do is replace row 3 by -row 3. Now I'm going a little bit lazy and do it here. So this would now be the result of that, right? Okay, so I have now also a 1 here. And now I need to make it in reduced echelon form. That means, remember, it always goes from, now you start from the back, from the bottom. So I'm going to use this one, the back, if you want, because the last pivot, right, to make these two guys 0. So the row operation I'm going to do, I'll do it in green, because this is one kind of not there anymore. So I'm going to do now row here. For that one, I have to do row 1, replace that -3 times row 3, and row 2, I'm going to just add row 3, okay? So we get, I need more space. Okay, and that gives me, all right, so what did I do? I multiplied with -3 this guy, so that's 1, 2, 0. So this was a plus now, right? So these are pluses, right? So it's -6 plus 5 is -1. The second row, I'm adding just, so this negative 3 plus, no, sorry, 2 plus negative 3 is negative 1, and I get 0, 0, 1, and I had a 2 there, good. Only thing remains is to make a 0 on top of this guy, so the row operation here is now obvious, it's row 1, row 1 minus 2 times row 2, and if I do that, I get 1, 0, 0, so we're multiplying with negative 2, so it's negative 2 to the negative 1, that's 2 minus 1, that's 1, 0, 1, 0, negative 1, 0, 0, 1, 2. And so these now are the coordinates. So what this means is, did I give names? Yes, this means that, let's call this purple vector W here, right? So this was my, or U, let's call it U. So now I'm saying is that U, where am I here? U is 1 time V1, that was the first of the vectors, minus 1 times V2, and 2 times V3. And again, we can check this, right? So if let's look at the coordinates here. So if I were to calculate the coordinates here, so 1 minus 1. Okay, so okay, where are they? Sorry, I get a little bit. Okay, so this was 1, 2, 1 minus, what was the other guy? 290, 290 plus 2 times 334. And U was 5 minus 1, 9. So this should not be true. 1 minus 2 plus 6, that's 7 minus 2 is 5, yes. And so you cannot check this is actually true. So these are the coordinates. So this gives me the coordinates. I mean, what I mean is, or rather perhaps saying 1 minus 1, 2 are the coordinates of U in this basis. This is not the standard coordinates, because the standard coordinates were 5 minus 1, 9 for U, but these are new coordinates in this kind of, if you would draw this, and there's pictures in the book, it's a little bit more complicated than our Manhattan grid here. You would have, instead of straight lines, you would have like lines that cross as, at angles, and of course this is only 2 dimensions. In 3 dimensions you would have even more complicated things. Okay, you can try to imagine. So we would have a coordinates. This basis would give me a coordinate system, what they call a skew coordinate system. And in this new coordinate system, this vector would now have these coordinates. Okay, so I'm going to assign homeworks, and then next time we will talk about basis of different spaces, not just R2, R3, and R4.